There's a bunch of us at USGS that are looking at this topic, but for this particular talk, it was Travis and Lori who helped me. And let's go on to the next slide. So I'm talking about this word applied science. And so what am I talking about? The definition, if you go on Wikipedia or someplace like that, is the discipline of performing scientific analyses for solving practical problems. And so what kind of practical problem are we trying to solve with Artemis? Not just Artemis 3, but overall with the campaign. It seems like a big one that distinguishes Artemis from Apollo, is the space camp, the sustained human presence. So it seems like that's probably a way to focus a very broad idea of applied science to, okay, what do we need to do to build toward a base camp? And as we were just talking, and Julie was reminding everyone, we're not trying to land in Artemis 3 at the place we're going to make the base camp. It might happen that way, but that's not the goal. At the same time, if after Artemis 3, we don't feel more confident about being able to pick a good place for a base camp, if we're not making progress toward that, probably feel like we missed something important. And in looking at this, one of the key things we ran into is there's no equivalent to the Artemis 3 Science Definition Team report that provides us comprehensive, community-vetted, prioritized lists of the experiments we need to do for applied science. There are some experiments in there that are building toward a basic understanding of multi-phase flow and reduced gravity and so forth, but it's not really focused on what do we need to know to build a base. And so next slide, given that we didn't have this nice document to build off of, we kind of went to what we're familiar with that seemed to provide a framework. So I'm not seeing the next slide yet. Yeah, so what we went to is the methodology for doing quantitative resource assessments. And the reason we felt that this was a reasonable framework to try to figure out what kind of experiments you might want to do is because it goes all the way from the basic science, the what are the resources, through getting a better understanding of the properties of actual individual deposits. And it also incorporates a lot of the technical and operational aspects of getting access to the resource, being able to harvest it, collect it, and then convert it into a useful commodity. And then all the way to making a report that's useful for making decision makers. So this going from basic science all the way to kind of programmatic decisions felt like it was a useful framework anyway for us to try to think of what experiments you might want to do. And so the next slide, we considered 3 types of resources. Julie just talked about ice. And there's a lot we don't know about ice right now. So a lot of what we need to learn is very much just the basic science. And so that's one end member. The opposite end member is solar power, where we have missions planning to use it because we understand where the sun shines. We understand how to convert sunlight into useful electricity, a commodity. And then in between, we picked regolith for construction, things like landing pads and so forth, where we know a lot about the regolith. There's still some questions about what it's like in the polar regions and specific conditions. And we have ideas of how to convert it into commodities, and we're working on those, but it's in between those 2 end members of ice and solar power. And so next slide, we're starting with solar power. Here's some of the questions. We know that our friends over in STMD are promoting and pushing for people to come up with clever ideas of big deployable solar arrays and so forth. So the questions become very practical about, can the ground support different sized arrays, they're moving or not, and how are you going to install it and deploy it? Are you going to land it from orbit and have it deploy itself there? Are you going to have rovers drive up the side of the hill and carry all the equipment there and install it there, so forth? So there's a lot of questions about trafficability. And so with those thoughts in mind, next slide, try to think of some of the experiments you'd want to do. And this mostly revolve around the geotechnical properties of the surface. So let's see, can we go to the next slide? Yeah, so there's obviously experiments that can be done using cone penetrometers or shear vanes and so forth to get really good measurements of the geomechanical properties of the soil. But one of the things that's different generally about applied science from more basic or fundamental science is that often in fundamental science, if you have a hypothesis you're trying to test, one really good measurement or a handful of really good measurements is the best way to test that hypothesis. In applied science, what you're trying to do is build statistics. You want to know how to design a system that's robust to the kind of variability you can reasonably expect. And so a handful of really good geotechnical measurements is very, very helpful. But you also want a lot of measurements in a lot of different terrains. And luckily, there's a practical way to get that. As astronauts just walk through different terrain, you're getting measurements, observations on the properties of that ground by how much are they slipping, how deep are they sinking into the ground. And so you can get a lot of information without doing a fancy experiment, but you do need to stop and collect some information, turn around and look at the boot prints, have the astronauts tell us how they're doing if they're encountering areas that are difficult to traverse. And so without a lot of extra effort, a lot of extra time, you can get really important information for applied science. But if nobody is thinking about it, then you'll never collect the data and you've lost that opportunity. And so that's one of the things that just thinking through this, just a little bit of awareness of what kind of information is useful could be really helpful to make sure we collect a good suite of data over a broad area without taking a lot of extra time and effort. Next slide. So then thinking about regolith for construction, a lot of the techniques that people are looking at really like the very fine-grained material and having that flow through to do 3D printing or stuff like that. Other ideas prefer coarser material. So it's important to understand the grain size distribution in the regolith and what controls that. We're interested in digging down and collecting reasonable volumes of material. So how do the properties change with depth becomes really important. And because we're digging it and moving around, what is the regolith like after it's been disturbed, is after it's been moved around? So not the natural undisturbed properties, but after you've moved it around, what is it like? These seem to be important questions. So next slide. So again, we're looking at a lot of geotechnical properties, especially before and after the area's been, I don't know, you can call it mucked up. And understanding what's happening, especially whenever we do anything in the third dimension with depth, trenching, coring, getting information about how easy that's going and looking at things just like the tailings, the stuff you dug out of a trench and the angle at which it comes to rest, the angle of repose of those, the stuff you dug up. This is all useful information. And again, you can do the dedicated experiments and those are very helpful, but there's also other information that if you just take a little bit of time to collect a few good images, a little bit of description of what's going on, there's a lot of additional really helpful information out there. And often the petrologists like to have coarser fragments from the regolith because you can actually look at how the minerals are interacting with each other and their relationship to each other. But for some of the stuff, we really want the very fine-grained material as well. So it's a slightly different emphasis. I mean, we know we want to collect cores of the entire regolith, all the fine-grained and the coarse-grained material. But for some of these applied science questions, that is more important than just getting the course fragments, which can be more important for some of the basic science. Next slide. And so then coming to ICE, the key thing is that we have missions going that will get there before Artemis 3 that will tell us a lot about the ice. And I think one of the key things, it's hard to predict what we're going to find exactly, but whatever we learn from those missions, it'll be important for Artemis 3 to help build that confidence that we can extrapolate from Prime 1 and Viper to other locations. And hard to say specifically what those experiments should be at this point. And so I'll just gloss over that one. And so, but it's going to be trying to understand the basic science and building a little bit from there. So I think what's in the science definition team's list of experiments for volatiles is probably covers most of the practical things we want to do for applied science as well. So next slide, just summing things up and repeating things. So many of the applied science experiments would be doing basically the same stuff as you're doing for basic science. However, we getting some specific supporting data, some additional data, information while you're doing those experiments can be very important and helpful for doing the applied science experiments. And the priorities for the different experiments can be a little bit different from the basic science and applied science. And the last slide I just threw in, if you can jump to the last slide, did look at all 13 regions very quickly using criteria that's just in my head. But it's pretty obvious, no matter how you want to cut it, that these 13 regions were selected because they're good for all these different questions. The real tricky part gets when you start to try to pick individual landing sites within them, and you have a limited distance you can travel from the landing site, it may be trickier to get to all of the different types of experiments you want to do for applied science. And so down selecting regions shouldn't be a problem, but when we start to talk about landing sites within the regions, that's when really need to start being very cognizant of what experiments you can and can't do. And I'll stop there.